Look at the skyline of any major city. Millions of square feet of glass stretch up into the sky, soaking up sunlight all day long. Right now, nearly all of that vertical real estate is completely dead space when it comes to generating power. The problem comes down to the physical materials we use. Traditional silicone solar panels are fantastic for rooftops, but they are heavy and completely opaque. You simply can't build a window out of them. Chemists tried to get around this by developing dye-sensitized solar cells. These work a bit like artificial photosynthesis, using special dyes to capture light. The early versions actually offered some transparency, but they relied on a metal called ruthenium. Ruthenium is rare, highly expensive, and toxic, making it impossible to scale up for citywide construction. The architectural ideal is something called building integrated photovoltaics. To achieve this, researchers need to design metal-free, organic photosensitizers that can be embedded directly into glass, creating semi-transparent, colorful windows that passively generate electricity. But designing these organic molecules requires balancing conflicting physics. When chemists modify a molecule to absorb a wider spectrum of sunlight, those exact same structural tweaks often trigger chemical side effects that destroy the molecule's ability to actually transmit electrical current. To build a better solar dye, researchers started with a familiar foundation, the iso-indigo core. This is a molecular structure derived from the same natural compounds that give traditional indigo dyes their deep blue color. To absorb more sunlight, scientists made a targeted modification, swapping the core's benzene rings for thiophenes. This worked perfectly, redshifting the dye's absorption up to 900 nanometers into the near-infrared spectrum, and producing beautiful blue, green, and purple hues ideal for architectural glass. But there was a hidden electrical cost. Those new thiophene rings drastically increased what is known as charge recombination. Instead of flowing out of the solar cell as usable power, the electrical charge would reverse direction and flow backward into the liquid electrolyte. Because electrons couldn't escape the cell, the physical performance collapsed. The power conversion efficiency of these specific thiophene-modified dyes dropped to less than 1%. It didn't matter that the molecules were absorbing vast amounts of near-infrared light. If the chemical architecture can't maintain a one-way flow of electrons, the energy is lost as heat before it ever reaches the grid. Faced with this complete electrical breakdown, the researchers made a counterintuitive decision. They abandoned the electron-rich thiophene rings entirely and reverted to the original, unmodified iso-indigo core. They realized the iso-indigo core possessed a hidden defense mechanism. When oxidized, this shape produces a massive dipole moment. That acts as an electrostatic shield, physically repelling negative charges trying to flow backward, keeping current moving in the right direction. This proves that in molecular engineering, you cannot prioritize color and light absorption over everything else. If the molecule lacks the chemical stability to hold and direct a charge, it fails as a solar cell. Even with the original core restored, the researchers faced one final, invisible hurdle. The iso-indigo molecule is strongly electron withdrawing, meaning it holds on to its energy very tightly, forcing the entire system to operate on a razor-thin margin. This chart illustrates the thermodynamic limit. The dye's LUMO level sits 0.25 electron volts above the titanium dioxide baseline, the absolute minimum needed to push electrons into the cell. If too much TBP tuner is added, the baseline rises, erasing the gap and stopping transfer completely. Operating this close to the thermodynamic limits of physics means there is zero room for error. A standard industry additive, used in standard amounts, is enough to accidentally kill the driving force and shut down the cell. By carefully mapping these exact tolerances, researchers figured out how to balance the original iso-indigo core with a highly specific concentration of TBP. The result of this balancing act was a specific new dye called 6-OTPA-iso. When tested in the lab, this optimized molecule managed to maintain the necessary electrostatic shield while holding on to enough thermodynamic driving force to achieve a 7% power conversion efficiency. 7% might sound modest compared to traditional silicon, but for a semi-transparent, metal-free window pane, it is a massive engineering success. By mastering the microscopic push and pull between optical absorption and electrical stability, chemists now have a viable blueprint for turning massive glass skylines into vertical power plants.